everyone. Thank you very much for joining us today for another edition of the SIMN Free Webinar Series. We are really privileged today to have Andrew Vietti joining us today to present his story on tailings from a metallurgical perspective. Just a quick bio for Andrew. He's the director of Vietti Slurry Tech and has a master's degree from the University of Natal. With over 30 years of sedimentation and dewatering experience in the mining industry from all over the world, he's definitely a catch for a speaker. Having initially spent 15 years in research at De Beers Consolidated Mines, where he implemented paste thickening technology, he subsequently became a director at Patterson Cook before co-founding Vietti Slurry Tech. He's specialized in clay, slurry, colloidal behavior, paste and filter dewatering, and for the different mineral types, both small and large operations. With tailings being quite topical, I think we can really look forward to today's discussion. Andrew is also a regular presenter at international conferences, so I can assure you that we can look forward to today's edition. Andrew, you can load your presentation and get ready, and we're all looking forward to today's discussion. Thank you very much for doing this for us. To the attendees, if you have questions, please use the Q&A tab at the bottom to pose your questions during or after the presentation, and we will curate some of the questions in a discussion format afterwards. Thank you very much.
Very much, Isabel. Thank you very much for that very nice introduction, and thank you everybody for attending. Today I'm going to be talking about paste and filtered tailings from a metallurgical point of view. And just to give you an idea of what we're going to talk about, I'll give you an idea of setting. We want to set the scene, why we want to talk about this subject from a metallurgical point of view, why I think it's important. And then we'll go into a bit of a history of paste and thickened tailings. We'll start off with the era of conventional and high rate thickeners, and then we'll lead into the rise of paste thickeners and end off with the promise of filtered tailings, and then some conclusions. So why do we really want to talk about this? Well, I think from my point of view anyway, you know, when people talk about paste and thickened tailings in a forum or in a discussion, it's largely viewed from a geotechnical point of view. And the metallurgical aspects, the dewatering processes are largely sort of a sideline issue. And there's a good reason for that. It's not just because people don't like metallurgy. You know, and ultimately in this field, the tailings engineers, the geotechnical engineers, they carry the legal responsibility for the tailings dam. They've designed it, they've operated, and if something goes wrong, they take the legal responsibility for that thing. So it's important for them. It's a very important subject for them. And then after the recent failures that we've all seen in Brazil, the International Committee for Mining and Minerals in 2019 initiated a global tailings review, which really focused on the geotechs, on how they operate these dams, what methods they use to build the dams, all the sort of the ways of looking at them, reporting on them, etc., etc. And also early days in paste and thickened tailings, there was kind of an initial design philosophy that was largely driven by the geotechs, saying that the design sequence of this tailing system is opposite to the process flow direction. So the geotech would say, listen, I need a tailings dam that sits at a 2-degree stacking angle, and for that I need the material to have a yield stress of so much. So the pipeline and pumping and pipeline guys had to design their system to handle that kind of rheology, and then it was expected that the thickeners would produce that material and it would all work. But in my experience, it's often not the case. It's often that the thickener gets put in and it doesn't deliver the density and the rheology that the pump and pipeline guys want, and eventually it ends up on the tailings dam that now the geotechnical engineers have to deal with this off-spec material and try and make a plan. So really, it's the metallurgical solid liquid separation unit process at the start of this whole chain that really dictates the success or not of the technology. And you know, paste and thickened tailings have been around for about 20 years or so, but it really hasn't taken off as much as it should have. And I wanted to go through the reasons why that is. So we start looking at the era of conventional and high rate thickeners. I'm going to take you back a bit of a history lesson to show where it's all originated from. So around about 150, 170 years ago, the first centrifugal pump was exhibited, I think, in France in about 1851. And then the big steps occurred in metallurgy. So Nobel and mining and metallurgy. Nobel invents dynamite in 1865. So that led to the possibility of large-scale mining. Then the ball mill and the jaw crusher were developed in Cornwall for the tin mines in 1880. And that kind of gave a big jump in the amount of material you could for the comminution phase. And then the really big one was flotation. The flotation recovery process started in Broken Hill in Australia in 1902, which then started the whole hydrometallurgical metallurgical process. And for that, then water was a big component. And so people started now having to think about recovering and recycling that processed water. So in 1905, John Doerr invents the first thickener as we would know it. And the design has largely remained exactly the same as that first thickener that John Doerr developed in 1905. There's a picture down at the bottom corner there showing a conventional thickener at the Bird Camp mine in Colorado about 1920. And it's something, as soon as you look at that, you recognize that unit process immediately. So from about 1905 all the way through to the early 1960s, thickeners were operated without settling aids. So the material settled and sedimented on their own. And it's quite important now that we define unit processes by their proper names, because people can get confused very easily. So a conventional thickener is a thickener that operates without any flocculant, and the material settles on its own account and very slowly. So you need quite wide diameter units, and we'll come on to that just now, so that the material doesn't get carried over, essentially. But from about the 1950s, late 1950s, the early 60s, the first synthetic flocculants were developed and started getting introduced into metallurgy. And so we define those thickeners that now use a proper settling aid, flocculants, as high rate thickeners, because the settling rates of those solids were settling so much faster than in conventional thickeners. The diameter of those units could be reduced quite a lot. So they called them high rate thickeners. And then just for interest, about 1985, the first Alcan paste thickener was introduced. So a conventional thickener is something like in those top photograph on the left, large diameters, up to around about 150 meters diameter, very low flux rates. That's the solids throughput, tons per square meter per hour. And they often had a center-driven rake drive, or when they got really big, they became peripheral rake drives because the torque and the mechanical integrity became such an issue. So after flocculants were introduced, we then call those thickeners high rate thickeners, and they obviously had much smaller diameters. The flux rates were orders of magnitude more than the conventionals, and they were generally center-driven. The drive was in the center of the unit, and that's kind of what the workhorse. 95% of all tailings these days are treated by high rate thickeners. And up into the late 70s and 90s even, people were using these high rate thickeners, but on a huge scale. So you can see the Ergo ones that are now running at the DRD plant. They are 137 meter diameters peripheral drives, and in big operations in Chile, Chuquicamata, also have massive thickeners, 131 meter diameter peripheral drives. And I'm mentioning peripheral drives because I want to come back to it later in the talk. So from a metallurgical point of view, what's going on? So this is a graph of quite nicely describing The performance of a dewatering unit in terms of water loss, cubic meters per ton of head feed. So obviously, as you dewater, you become more efficient, you thicken the underflow more, you recycle the water better, so you use less top-up water. So your water loss curve starts dropping down, becomes more efficient. And at the same time, your underflow solids concentration gets thicker. And a nice way of describing the thickness of the underflow is the sheared yield stress of that material. So this is a curve particularly for diamond tailings, because I've got a lot of information on it, so it makes sense to me to do it on diamonds. And so, you know, if you were a typical platinum miner or a gold miner, you would say, well, 40% solids concentration, you've got no yield strength. But this is because in diamonds, the top size going to tailings is quite coarse. It's around about, can be up to 1 millimeter in some cases, or generally about 500 microns. So when you've got a slurry at 500 micron top size at about 40% solids, it's still quite watery. So just looking at the 2 unit processes there, conventional thickener going down to high rate thickener. In the case of diamonds, you know, at a conventional thickener, you get about 30% solids out the bottom. High rate, you can get easily 45%. But if you look at the rheology of that underflow, it's still pretty watery. It's got no yield stress. So it behaves as a Newtonian fluid. So it pumps like water. And that's quite useful for the geotechnical engineers. So they use those segregating properties of the slurry, of the non-Newtonian fluid, to actually develop their construction methods. So in this slide, you see 2 construction methods. The one is the now ubiquitous and kind of controversial upstream method, where you build a wall around the perimeter of where you want to contain this tailings. And then from the top of that wall, you deposit into the dam. And because the material is segregating, the coarser particles settle out very quickly and they form a beach. And then the finer material and the water gets carried on to the middle of the pond. And that beach with the coarser material is a stable structure, and that kind of holds the whole containment area together. The other method is called downstream, where you build a starter wall, and then you use something like a cyclone to classify the material. So the coarser solids are then deposited on the outside of the wall, and the fine stuff gets deposited onto the inside of the wall. And that's probably a lot more stable, but also it's a bit more expensive to operate. And you know, that upstream method has been used extensively and very successfully, especially in South Africa. And this is an example now of a typical, what they call a ring dike upstream TSF, tailing storage facility construction. And you end up with a containment basin, essentially, where the walls are holding the structure together. It's got a concave profile, and in the center of this basin, you contain the fine solids and any water that might accumulate. So these things were operated very successfully right up until sort of the early 70s or so, when things started to change. And the reason and the question is, why did these start to change? Why did they start becoming a bit more risky? So it goes back to really the demand for minerals and commodities. So you can see in these two curves here, this is the world iron production on the left, world copper production on the right. But from about the 60s, the demand for these metals started rising exponentially. So there was a huge demand for metals and from mining. And at the same time, the ore grades were becoming poorer. So the general trend was that the ore was getting less rich, but there was still a massive demand for the metals, and so production volumes just had to increase, and obviously then tailings volumes increased. So this is some very interesting little comment that was made by Andy Robertson, and Andy Robertson is the owner of Robertson's Geoconsulting, but more importantly, Andy was one of the co-founders of Stefan Robertson and Kirsten, SRK. And in 2012, he said, The largest mines have increased their production in terms of tons milled per day by an order of magnitude each 30 years for the past 120 years. That's quite an interesting comment. And if you look at this curve where we've got time versus production, about 1920, in the early 20s, they were treating around about 100, 200 tons a day. That was the total production. And every 30 years or so, it's been increasing up till today, where the largest production, the largest mines and metallurgical plants out in Chile are producing in the order of 100,000 to 250,000 tons a day. That's 1 million tons treated every 4 days in some cases. That's a huge volume. And at the same time, if you look at the world mine tailings failures, starting around about the 60s, things started increasing. So before the 60s, there were sort of few tailings dams disasters in terms of very serious and serious failures. But in the past, since the 60s, you could say the numbers have been doubling every 20 years or so. And we can see the effects. So talking to some very experienced geotechnical engineers, one of the reasons it seems to be is that the dams, the TSF's rate of rise in terms of rise of meters per year, in the olden days was kind of very low, and so the risks of failure were kind of very low. But with the more higher tonnage, these rates of rises have been increasing. And obviously the higher the rate of rise, the higher the rate of risk as well associated with it. And we end up with more recently having a number of very serious tailings failures with the conventional method of thickening, high rate and conventional tailings disposal methods. So for instance, Mary Sprague, and they all seem to be related, sorry, just going back, they all seem to be related, not really to the technique of building the dam, but to the very fact that there's a lot of water contained on that dam. The presence of water makes these things unstable. So Mary Sprague in South Africa in '96 failed because that particular day there was a very heavy downpour of rainfall, and the pool was quite big, and it managed to breach the side wall of the dam, and the whole contents failed. In Hungary, a red mud tailings dam failed, not because the containment structure was weak. In fact, the containment structure was made out of fly ash, which is kind of a very weak cement, you can say. But because the water on the dam seeped under that corner there and started eroding away and caused the failure of the wall. Mount Polly, the same thing. The foundations of the tailings were built on glacial till, which failed. And then obviously Brumadinho in Brazil, which was another failure because the dam also had a lot of water. The jury's still out on that one, but I'm sure it's going to come down to something like that. So now, what can we do? So this is now the rise of paste thickeners. Well, the concept there was to develop a thickener that could dewater more efficiently to generate a stiffer tailings product. So if we have a look at our graph again, you know, if you were to feed kimberlite tailings to a paste thickener, you would end up with something in the order of around 60–65% solids. Now at that stage, you've got a yield stress and in the order of around about 90 pascals. And that difference now, the tailings there are non-segregating. So they do not behave as a segregating slurry. They are now a non-Newtonian fluid, and they have different flow properties. So the first reference of deep cone thickener was made in the British Coal Board in about 1972. And looking at that little diagram, it's quite amazing at how close they were to the real product in the end. So they had a steep-sided cone, about 45 degrees, greater than 45. On the rake, they had what we call pickets. In their case, they called them stirrer. Those enhance the consolidation properties of the mud bed. So instead of just relying on gravity to densify the mud bed, they introduced these stirrers, which could then have a little bit of shear onto that mud bed, but release the water. And so you get kind of an accelerated consolidation, get higher solids density quicker. And then in their idea, they wanted the underflow to be put onto a conveyor, which was really far-thinking thoughts at that time, which would be ideal if it was really true. In what we found over the years is that taking a paste thickener material and putting it onto a conveyor really isn't feasible, because it's not really dry enough. So where was it first applied? Well, the first applications found themselves in underground backfill applications using cemented full tailings. So in South Africa, people are familiar with backfill on the gold mines, where they use it's called hydraulic fill, where the tailings are basically classified. The fines are taken out, and only the coarse material gets pumped underground, and it goes into the stope, and then it builds up like basically a beach sand. All the water runs out, and you're left just with the sand. But in some cases, you need the full tailings because you need the extra tonnage to go underground. And the only way you can do that is to take the full tailings and thicken them up, and then add cement. That's called cemented tailings. And the first application of that was at the Bad Grund mine in Germany in about 1971. And they achieved the paste probably by filtering their tailings. And then they added cement to that. In Inco in Canada in the early 1970s as well, there was a mining engineer called Dave Landrio, who was very interested in paste backfill. And he actually developed his own thickener. He developed this thing called the paste production and storage mechanism, where you could prepare a thickened paste and then keep it moving like in a concrete mixer with that scroll. So they could add cement and keep it mixed until they needed it pumped down to the stope. The first surface applications were in the 1970s as well, surface tailings disposal applications. And that was accredited to Eli Rabinski, who was a geotechnical engineer, very far-sighted guy, who introduced the first paste tailings design at the Kidd Creek mine in Canada in about 1975. The reason he did that was because he was forced to look at an alternative method, because the Kidd Creek mine in northern Ontario is located in an area where there's lots of muskeg. It's like a peat. And he needed borrow material to build starter walls of this dam, and there wasn't any available. So he thought, well, if I could thicken the tailings sufficiently enough and discharge it from the center of the dam, I could build a self-supporting hill, like you can see in the picture on the right, in which it could be contained in small bund walls, and you could basically essentially let that dry, and it would be fantastic. So his idea, he did that, but the thickening, the dewatering processes that he had at the time were only high rate thickeners. He started off with a conventional thickener, and then they put in a high rate. So it wasn't really very successful. It was in terms of its efficiency, but it was still the very first one. But now, getting into the 80s and 90s, the first applications for surface tailings disposal and the first ventures into making a thickener really came out of the aluminium industry, the alumina industry. And the two rivals there was Alcan in Canada and Alcoa in Australia. Very secretive industry. They kept all the information to themselves. They didn't want any competition. So Alcan really developed what they termed a deep cone thickener. And they installed it in all their processing plants, actually. They tended to be quite small diameters, sort of 10-meter diameter or less. They had a steep cone of about 30 degrees, high sidewalls. They had rakes with pickets on them, and we called those low-profile rakes. And they came up with a really ingenious method, because they knew that if this material got thick enough, how do they get it out of the thickener? It became a big issue. So they developed what they called an underflow shearing system, so that the unsheared material in the tank would get sheared at the bottom of the thickener, so it would flow a little bit easier to get it out of that thickener. And they had a central drive. The rake was driven centrally because of the diameter. The diameter of the thickeners were quite small, so they could get away with a central drive. Alcoa, on the other hand, developed a high-density super thickener, they called it. And they took existing thickener design and they basically made it stronger. So in Pinjarra in Western Australia, they installed this thickener. It was a 90-meter diameter, big unit. It was typically of the high rake design, so shallow cone, low sidewalls. They didn't have any pickets on their rakes, but because the rake was a box truss structure, those trusses really acted like pickets. And they had a peripheral drive, which was very interesting because they anticipated very high torques. And so they have, if you can have a look at that thickener there, there's a little buggy that runs around the outside of that thickener, which basically turns the rake around. It's a very interesting design, but in their application, it was good, but for the smaller metallurgical operations in the world, it might have been too big at that time. So people started focusing on the deep cone. But anyway, both companies also developed their own methods for TSF construction. So they developed what's called a central thickened discharge, or a CTD method, where the thickened material comes out in the middle of the dam through some sort of a fountain device, and it basically flows away and forms a hill. So you could see down at the bottom there what the profile looks like. And then the alternative method was what's called thin layer deposition, where you would deposit over a wide area the thickened tailings, so it kind of spreads over the land, and you layer it in thin layers that dry out. And this gave rise to also what's called down valley deposition. If you've got a valley, and you could still also add it, and it would run down to a sort of toe wall. So by the early 2000s, some Australian geotechnical engineers were already designing central thickened discharge dams. But again, the dewatering equipment was lagging behind. They all kind of had high rate thickening to develop the product, to generate the product. So the two places we looked at there in the pictures, there's Peak Gold Mine. You can see in the distance there, there would be the point of discharge, and then it kind of flows away. But you can see the material flows over a big distance, because it's not really thick enough to be contained or build anything of a structure. And this is quite an interesting one. Mount Keith nickel mine in Australia. They had a very ingenious way. They had, I think, they had a central one in the middle, and then 9 different rises around the edge to try and make a sort of hills in the landscape. And that was what ultimately they wanted to achieve. But again, thickening technology wasn't there, so they didn't really generate these steep hills. So by the early sort of 2000s, the two main paste type thickeners had emerged, and these were the so-called deep cone paste thickener, which is more of as you can see in the picture, it wasn't very big diameter, more high sidewalls and a 30-degree cone angle, and then what's called a high density paste type thickener, which is more of a conventional design. So where were these the applications in South Africa? So this is one which is very familiar to myself. It was the ex De Beers operation at Kimberley, the central treatment plant, which is now the Kimberley Ikapa mine joint venture plant. And that was commissioned around about 2000, 2001. And it was for treating diamond tailings. The feed solids tonnage was relatively high, 600 ton an hour. So there was 550-meter diameter deep cone paste thickeners installed, underflow solids concentration around about 60% by mass. There were 3 positive displacement pumps to pump that tailings over a 5.5 kilometer distance to the deposition site. And it was a central thickened discharge method, which many lessons were had on that one before we actually got it right. And this is some photographs of the site at the deposition point. And again, very clever geotechnical engineer came up with this system, which is unique South African design, which he calls the wagon wheel. And the idea here was to be able to distribute that tailings around that point of discharge, because previously the material would just flow wherever it felt like it. And what he did was he took advantage of what's called the plunge pool. So there's a pipeline that runs underneath this ramp, and it elbows up here, and it basically open ends there, and the tailings flow out like a chocolate fountain in a way. It was quite nice. And it forms a plunge pool. And then he put spokes on this plunge pool with these half pipes, and then these half pipes were then blocked with sandbags, and he would then lift that, and it would allow the flow to go in whatever direction he wanted. So that's a very nice design. There's some nice picture of how this material flows out. And you can see it flows like lava. It's fantastic. Very little runoff water, and it dries very quickly. I've got a small video of this here, so we'll go through that quickly. Play it quickly. So that's the end of the pipe running into the plunge pool. And you can see there's no water. This dam is dry. And there were obviously flows in this direction at some stage. It's a bit noisy because of the wind. This is where they were flowing out at one, and then they let it dry. And there you can see the tailings tunnel, where the new material is coming out. Okay, so yeah, that gives you an idea of how it worked. This is the deposition site. So it was built on two old existing tailings dams. So this is the perimeter, but there's the old tailings dams, those squares there. The pipeline came from the plant there and then split into two branches, and they both ended there and there in case they needed to change the deposition point. So it was commissioned in about May 2002 over quite a big area. It's a 380 hectare site. But the important thing is that this site has been running for 18 years and it's had one wall lift in all that time. So after all those tonnage that's gone into that dam, nothing, they didn't have to put a new dam or anything like that. It's still running fine. Okay, so with all that, why then are paste thickeners not more widely used? I mean, we know that probably only about 5% of the tailings are treated by paste and thickened tailings. And, you know, after I've thought about this, and it seems like there's two main reasons for that. And let's go through those. So one is the tank diameter and the aspect ratio for large tonnages. And when I talk about large tonnages, I'm talking about 2,000 to 4,000 ton per hour treatment capacity, which is really limited to the big copper mines in Chile and Iran and maybe the US. So in the early days, before 2000, when CTP was designed and commissioned, the diameter of a deep cone paste thickener was the maximum you could get was about a 15-meter diameter. They were too scared to build them larger. Nobody had ever done that. So we were limited in terms of number of tanks, in terms of diameter and numbers of tanks we could get. Then the first big operation, Sarchezmi in Iran, was designed and built, and they could only get 24-meter diameter thickeners. So it had gone up from 15 to 24, and so they got 12 24-meter paste thickeners in at that stage. Finally, then in the sort of 2013-14 or so, at the Centinela copper mine in Chile, we managed to get of the order of 45-meter diameter. So they put in 3 45-meter diameters. But let's have a look at some pictures here. So this is the picture on the left is Sarchezmi's feed distribution manifold. That's for 12 24-meter diameter thickeners. So you can see it's a piping nightmare there to get even feed to all of those thickeners. And then even the big diameter thickeners, with that 30-degree cone angle, when the diameter of a thickener gets large, you basically end up with it looks like a massive pancake with a huge cone on the end. And you need enormous structural capability to hold that steel work up. So it kind of becomes impractical to have this thickener, the deep cone paste, for very large applications. And it makes more sense then to go for the high density paste kind of design. The other one is what I've called the small matter of rate torque. And this is quite important when people start talking about definitions again. In most definitions, when you see a yield stress curve, it's the sheared yield stress curve. So because the pump and pipeline designers and the geotechnical engineers, they deal with material that's gone through a pump and it's been sheared all along the pipeline and it ends up at the tailings dam in a sheared state. So they're interested in the sheared yield stress of the material. While the thickener guys are more interested in the unsheared yield stress of the material, because that's what the rake and the rake gear drive sees. So for a typical paste material, it's got a sheared yield stress of about 100 pascals at a particular solids concentration, which would be, let's assume, the design solids concentration. When you look at the unsheared yield stress, that can be at least 2 or 3 times orders of magnitude greater than the sheared yield stress. So what the rake drives has to see is huge yield stresses, and so the gearboxes have to be really, really strong. And now it becomes quite interesting, because the way that is conventionally in the industry is calculated or designed the size of a gearbox for a particular application is using this very simple equation called and it's come from, we must remember now, it's quite important to remember that these calculations were derived in the days of conventional and high rate thickening, where the slurry that was generated tended to be a non-Newtonian fluid. It didn't have too much or if it did have any yield stress, it was pretty low. So the calculation states that the maximum operating torque is defined by K, which is really an empirical number that was developed by the early thickener guys, times the diameter squared of the tank, times a factor which brings it to SI units. Now, in paste thickening times, the K has been approximated or been replaced by the approximate unsheared yield stress of the underflow at the target underflow density that's required. So you would go into the lab, you'd measure the unsheared yield stress of the material at the target or the design underflow density, and that would effectively be K. And at the bottom graph, I've shown the torque requirement, and we're talking in million Newton meters here, against tank diameter and at a particular solids, and I'm assuming a K factor there of an unsheared yield stress of 250 pascals. So for a 50 meter diameter paste thickener, you require something close to 10 million Newton meters. That's what has been known as the maximum operating torque. Now, when the thickener goes in, the thickener vendors then tell the operators, listen, you cannot run the thickener at 100% of rake torque, because your bearings and your gear life of that gearbox will be reduced to a few days. So to operate and keep your gear life for a reasonable length of time, you operate typically at between 25 and say 40% of the MOT. So they tell the operators to run, which is called the normal operating torque, down there. So in this particular case, the operators would try to keep the torque down at about the 5 million Newton meters, which is way below what the actual the slurry requires. And this seems to be a hangover from the old ways of doing things, and I don't think this has been properly understood or updated for paste thickeners. And so in my experience, you often see many times that a thickener is designed based on test work to achieve a certain solids concentration. When it's installed, the operators cannot achieve that underflow solids concentration, because as the material thickens up towards the design density, the yield strength picks up, and suddenly the rake can't handle anymore when it's operated at 30% of the maximum operating torque. And we've seen it where in big thickening operations, if the rake trips and bogs down, that whole mine is down for at least a week until they dig out that thickener. So the operators are basically threatened with complete dismissal if they stop the rake. So they tend to operate way below where they should be operating. And ultimately what happens is you get a lower underflow density going out to the tailings dam. cause all sorts of problems at the tailings dam. So this is for a central drive. That blue line is for a typical central drive. But on a peripheral drive, you can almost run at 100% because the stresses are so much less as you drive it from the periphery. So it's very important to start looking at periphery drives again. And just to bring this, this fact home, in a particular mine, there's 3 60-meter diameter high-density paste thickeners with central drives. And the data at the bottom there that you can see was taken over a period of time, looking at the underflow solids concentration generated by those thickeners versus the rate torque that they were operated at. And the design underflow solids concentration that the mine wanted to achieve was around about 69–70%. But these guys were told never to run more than 40% of the rate torque. So they basically ran within this range. And as the underflow density picks up, it's tending to go to there, but it's been cut off because the vendors, because the operators were told never to run above that. At the same time, some work was done by Ototech on a small thickener, a little pilot scale thickener, where it showed that they could get higher densities and achieve their design density, but you would have to have much higher rate torques to achieve it. And in fact, the 80–70, you were talking about running continuously at 100%. So the calculation to it is correct, but it's the application of in the field. So what ultimately we have to do is look at bigger torques for these paste thickeners, central drive paste thickeners. So going full circle then, for very large tonnage operations, it's probably better to go for a high density type paste thickener design with a peripheral rake drive, like was done in the early days. And you have to go through these lessons and learn your lessons and then look back and say, oh, well, the guys did have a good idea in the old days. For smaller applications where you don't need such large diameter paste thickeners, then probably look at larger central rake drives with higher rake torques. And then obviously link torque to control, because that was probably the best control method you can go on. So where are we now? So we're looking at now in the aftermath of Brumadinho. So the ICMM initiates a global tailings review, develops what's called a positioning statement for the governance of these TSFs, which is really all about how people look after them, how they checked, checks and balances around these dams. Not too much really on the dewatering technology. And then most of the major mining houses have now all disclosed all of their TSFs, how they run, what kind of methodologies are used to build them, etc., at the request of the fund managers, really. And this has given a huge impetus for pushing filtered tailings and dry stack tailings. So suddenly, after that massive disaster and all the dust that it caused, everybody started focusing on ignoring paste but going straight to filtered tailings. So really, what is possible? What is metallurgically possible? So it is possible to filter anything, really, as long as you've got big enough filter pressure behind it. So this is an example of filtered tailings for kimberlite. You can get way down and high percent solids, 80% solids, and massive water recoveries with a pressure filter running at about 10 bar pressure. And in this case, your yield stress would be in the orders of kilopascals. So that's now thick enough to go on a conveyor belt. So we've got two extremes now. You've got paste thickener, which can give you something where you can still use a pump, but on the pressure filter side, pumping is not an option anymore, and you have to go conveying. But between those two zones is something which I call the danger zone. So anything higher than about 500 pascals, which is difficult to pump or almost impossible to pump, but lower than about 2 or 3 kilopascals, or 1 or 2 kilopascals, it looks thick, but it doesn't behave thick. So it looks like something like that. So this material, as soon as it's come out of a filter, looks pretty good and looks like it can convey nicely. But as soon as you put it on conveyor belt, it starts to fall apart, and it's too thick to pump also. So there is some sort of a danger zone that the metallurgists really have to be aware of, and what transport method they need to look at. So what are the mechanical unit process requirements for filtered tailings? Well, you need a thickener before the filter, because filters like something that's relatively thick. They don't like a very low density slurry. So you would have to have some sort of thickening device. Then you would have your filter, and then a conveyor and a spreader to spread that material. And obviously capital costs then come into it. So this is just a relative comparison of capital costs there. High rate thickener, if it was 1, the high density paste thickener would be about 1.5, deep cones about 2, and the filters about 4. So you can see costs rack up very quickly when we look at in filtered tailings. And it's used, where is it used? Well, I've seen reports where it's only used in about 1% of all tailings disposal applications. And it's typically in areas where raw water is not available or extremely expensive. So, and when we talk about extremely expensive, it's more than $3 per cubic meter of raw water, or where the need for product recovery is very high. And it's relatively small tonnage operations. So the two at the bottom there, which are most quoted, is La Coipa gold mine in Chile, which is a completely dry and filtered tailings operation. And then one much closer to home is this Scorpion zinc operation in Namibia, where they use filtered tails and then deposit it using a conveyor belt. The largest treated plant now apparently is treating about 1,200 tons an hour, which is really, it's quite a big tonnage for filtered tailings applications. So the limitations really are the mechanical side of things, which I think are improving greatly. Now you get machines that are treating, each machine can treat between 300 and 400 tons an hour. So examples are the FL Schmidt Colossal unit, which is, I think it's each plate is 4 meters by 2 meters. They're now also developing something that's it's astounding. It's like 5 meters by 3 meters, I think. And then the Metso VPX series also can treat these massive tonnages. And the other thing is, you've got to look at the slurry properties. If you can play around with the clays which are contained in these slurries, you can increase the permeability, and then you don't need so many machines, and it's a lot easier. You don't need such high pressures, etc. So if you can condition a slurry from an unconditioned state chemically in the process water, you can change something that's difficult to filter to something that's probably easy to filter. So a lot of information there, but let's just go through some conclusions. So really, we can see that in the past 20 years or so, dewatering technology has advanced greatly, much greater than the previous 20 years. And on the paste and thicken tailings side of things, we can still see there's room for improvement, particularly on the rake torque drive issue. But I think once that's ironed out long term, I can see that, and people gain confidence in it, then I can see paste and thicken tailing becoming kind of the bulk standard method for dewatering tailings. On the filtered tailings side, there's still a lot of learnings to be had, I feel, and there's probably a lot of lessons to be had. I think it's great for niche or smaller applications, but in longer term, for large applications, we're going to see more of these hybrid paste filtered methods where you paste maybe 70% of your tailings, you filter 30% to achieve a kind of optimum that you need. Yeah, so I think overall that's the end of the presentation. I'll take any questions if there are any.
Andrew, thank you very much. As a pyrometallurgist, that was very enlightening for me. I learned a lot. So we have a very interesting comment here as well in terms of, so Harman Otterdam asks, he says that if you, in a poorly designed situation, you also increase the pollution of the water, especially when you recycle it in the plant. Do you agree with that comment?
Yeah, there's a lot of you know, as you thicken up, you recycle more and more efficiently, and at some point you're going to really start increasing the salt load in the plant, which might have a detrimental effect on other metallurgical processes like flotation or whatever. So that's getting more and more attention these days, and will get more with filtered tailings especially. So you do pollute your process water, which then means that you have to have some sort of a water treatment plant to take out those pollutants. Yeah.
Yes. Then there's a comment here from, first of all, a comment about saying a powerful presentation, which I just agree with. And at the danger zone, the question is, what possible transport mediums can you suggest? Or is it something you completely have to avoid?
Sure, I would avoid it at all costs. Yeah, you know, you can maybe start talking about trucking, you know, like maybe train wagons or something. But yeah, I think it's a very messy and a very dangerous area to be in. Yeah.
So like a screw or an Archimedes principle or something?
Maybe, yeah.
But it's not ideal. I mean, I've worked with stuff there before. It's really hard.
No. Look, we've tried to put paste on at 65 or 70% solids on a conveyor belt. It looks great, but then over the first one of the first tipping points or whatever, anywhere, it's just going to create a huge mess, and it shears also. It shears down.
Like there's inherently a vibration in a conveyor, so you're going to clean out the water. Yeah. So there's a question from Henry's saying, how about hydrocyclones? Is there a role for those?
Look, hydrocyclones, there's another misconception. Everybody thinks they're dewatering units. They're not really dewatering units. They're just classifying units, okay? So hydrocyclones are great for, if people think, the idea is I'll hydrocyclone my tailings to a thickener, because then I'll remove some solids from the thickener and remove the load of the solids to the thickener, which sounds great. But the problem is you end up by making the feed size distribution to that thickener finer, which makes it more difficult to actually treat. So I think there's a place for hydrocyclones, but you know, don't confuse them for solid liquid separation devices.
Yes. So I'm just trying to understand the question. It's saying you've looked at applications for copper and aluminium, and what about coal? Is there a difference?
Coal would be a great material to put in a paste thickener.
Yeah.
You know, it's got lots of clays, etc., in the tailings, and so that would, as long as you know you go through the proper test work or whatever, it's a great material to thicken up. There's no issues with, you know, most tailings will be fine for a paste thickener.
Yes. So Harman's saying, if you're in the danger zone, is it better to just add water or make it thicker by adding dust? Which way would you go if you end up in that situation?
Yeah, making it thicker with adding dust might be a good idea. I mean, if you've got the available material, then you just you add it in and like a plug or something, higher solids concentration, then possibly it's conveying. It's a bit of a bad thing to take something that's thickened and then dilute it back down to pump it. That's the issue.
Yeah. But thickening it up further might be an option.
Yeah.
Would you get this the shear strength in coal issue come up? Is from Gerald.
Yeah, look, I mean, coal tailings are very similar to kimberlite tailings. As you will, with a paste thickener, you will get it up to, it's, you know, I can't give for every material will thicken up to a certain solids concentration. So you can't say it will thicken up to 50% whatever, but it will thicken up to something that's got a fairly decent yield stress, at least, you know, 70 plus if it's in a paste thickener.
So in your, we were talking about the control. So Steve is asking, have you come across any applications where the control of the feed solids has found success? The percentage solids obviously plays a critical part.
In a thickener, the feed solids concentration really relates to the flocculation process. So it's important to keep your feed solids concentration within a certain window to get, decent flocculation so that your floc doses don't go through the roof. As far as operating of the thickener is concerned, in terms of trying to get the right density, no, I don't see that being a critical parameter for that. No, it's more a case of residence time, raking, and torque. Those are the issues.
So there's just a general question. What do you think is the most likely hazards associated with this technology?
Likely hazards?
Yeah, what is your most likely hazards?
For paste and thickened tailings? The worst hazard is that people don't have a good understanding of it and then apply it wrong.
Yeah.
I've seen funny story in a big paste application in Chile, where they installed big paste thickeners and they designed the dam for this high thick material. And when they commissioned it, the geotechnical engineer said to me, they expected the toe of the tailings to arrive at the dam wall, which was like in a down valley deposition method, to take about 40 years. And after the plant was commissioned, it took 40 minutes because the thickeners didn't thicken as they should. So, those are the big dangers. That's the big danger for me.
Yes. There's from Anthony Siebert, he's saying, thank you for the presentation. And then Africa has iron ore deposits which are remote with no railroad infrastructure, using very long slurry pipelines to transport product to port and then to return the water have been looked at. Have you had any thoughts on how this would be best accomplished using thickness to pre-treat, or what new technology are being developed for this?
You mean for iron ore concentrate, essentially?
Yeah, over the long distance transportation, yeah.
Look, I think pumping iron ore and that has been done, and yes, it is expensive. The other way is how would you move concentrate over a long distance? Paste thickening to give you a high thickened product, but you still have to get it somewhere, and it's difficult for me to say. Filtering it, then you have to transport it by train or truck or something like that. Yeah.
It's probably one of those where we say that, what they figured out is pumping slurry over long distances is probably the solution.
Yes.
I don't think that anybody's come up with a better way.
No, not for concentrates also. I mean, concentrates, remember, a lot different from tailings. So the higher densities, they settle very easily. You need high velocities, etc. Yeah, it's quite a different game.
So here's a practical question. We're sort of running a little bit out of time, but I'm going to try and fit in a few more. So Marty says, I have dealt with high flow thickeners, but struggled with the underflow pump choking due to the coarse particles. Is there anything that can be done to amend the design to accommodate this? So
coarse particles settling in a thickener is, there's a number of reasons that could be that, because they would tend to settle up first because they're the heaviest particles, and if there's no mud bed to entrap them, they will sediment out and form a sediment at the bottom of the thickener. So there could be a whole bunch of reasons there. One could be that you're not flocculating properly. One could be, she says high, what thickeners were there? High flow rated.
High flow thickeners. High
flow thickeners. So it could be that you're not building a bed. There are cases where in some thickeners the feed volume coming into that thickener is so huge that it gets channeled down the feed well and basically erodes the bottom of the mud bed continually. So there could be a number of reasons that could be affecting that, causing that.
Okay, so it requires more investigation and more information. So if you're looking at conventional methods of building tailing dams, would there be any changes on how you would construct your TSF when using paste thickening, considering that you might have limited space available to construct your storage facility?
So Paste, you can deposit paste in a number of ways. You can put it in the central stick and discharge method, or you could distribute it from the outer sides like they do with spigots around the perimeter of the dam, like they do with upstream method. So it is possible. It's not as though just because it's paste now it must go in the center. Big mines in Chile deposit from the outside, and they just basically form these, try and form these thin layers that can flow down and dry. Yeah, so it can be done.
And then, are there any paste thickening examples using fly ash?
Fly ash paste, not that I know of, no. But fly ash can be pasted.
And then, is this technology tested in PGM processing, or would you recommend it for PGM tailings?
Sure, for sure, definitely. Absolutely. I think it's applicable to any tailings, you know.
Yeah, yeah. There's two questions asking about centrifuges. Is there any application for this? What is your view on it?
Centrifuge is a good application. Only problem is that it's not a massive tonnage of a unit process. So it's got its niche applications. I think in small tonnages, 100, maybe 200 ton an hour, then absolutely. It's nice and portable. It uses a bit of power, that's the only thing. But it's definitely got advantages. Yeah.
So, Andrew, I think that will bring us to the end for today. We're running a little bit over time already, but first of all, thank you very much for all the interesting information and background. So, as I said, as a pyrometallurgist, that was completely new area for me to learn about.
Excellent.
And I always enjoy learning. And it was an excellent presentation, very professional. We really appreciate your time. I'm sure we can share this with our attendees, the presentation, if you don't mind.
No.
Thank you so much. Thank you everybody for attending, and thank you very much for your time, Andrew. We hope to see you here soon.
Thanks very much. Bye-bye.
Thank you. Goodbye, everyone.